Okay, I want to offer this up as a review for exam 3, and I'm going to go over all the problems, but this will not be supplied onto Canvas. So let's work this, and this should prove to be very, very useful. Okay, again, this will not be provided on Canvas, so pay attention and take note of each problem. I'm going to go pretty slowly. There's quite a few problems to discuss, and let's go. Now, this first page deals with exponentials and logs. So look at this. It says find the exact. Exact means no decimals. It's just another way of saying no calculators. So if you look at part A here, this is log base 10. Well, this can be rewritten as log base 10, and this is 10 to the fourth. And of course, when we have log base 10 of 10 to the fourth, this just results in 4. Now in part B, log base 36 of 6. Well, see, this can be rewritten as log base 36, and 6 is 36 to the 1/2. In other words, 6 is the square root of 36. So this is just 1/2. See how easy these are? This is money in the bank. This problem, I'm going to go out here. This is log base 6, and this is 1/6 squared. Well, this is log base 6, and now 1/6 squared, 1/6 squared can be written as 6 to the -2. So that's just -2. Natural log of 1, 0. Natural log of e, 1. This is log, this notation, ln means log base e. So we have log base e of e, which is just 1. That's e to the first. Those problems, folks, are gifts. Don't miss those. Now here we're just wanting to use properties of logarithms. So I've got a lot of stuff in this problem, but what I've got overall is a quotient. The parentheses look kind of funny, don't they? So let's break this up. It's going to be the log of the numerator. And let's see, that's going to be an x cubed e to the 7th minus the natural log of yz. Okay, now look at what we've got. Just look at the first one. I've got the natural log of a product. So that's going to be the natural log of x cubed plus then the natural log of e to the 7th power. Minus then, and you got to have those parentheses. This is going to be the log of y plus the log of z. Okay? And finally, the natural log of x cubed is 3 natural log of x. The natural log of e to the 7th is just a 7. And this is minus log y minus log z. There's only a handful of properties for exponentials and logs. And if you know those, you can do a lot of problems. Now, problem three here is the reciprocal, the inverse of this. Here we took the natural log of a complicated expression and wrote it as a simple linear form involving logs. Here we've got the linear form, and we want to go backwards. So first of all, I've got the sum of two logs. That means log base 2 of the product of x minus 2 times x plus 2. Okay? So I'm going to combine those as a product minus log base 2 of x plus 3. So I've now got this log minus this log. So this is going to be log base 2, x minus 2, x plus 2, x plus 3. So problem 2 is using properties of logs in one direction. And then problem 3 is rewriting a log expression going the other way. Now we did a couple of these in class. And the trick is to pick the middle power and let's say, there's two ways to do this. You could let a equal e to the x, and then a squared is e to the x squared, which is e to the 2x. So if you do that, then this becomes a squared plus 3a minus 40 is 0. Now, what are the factors of 40 which subtract 2, 3? Well, they're 5 and 8. So this is a plus 8, and then a minus 5. So we get a is minus 8, or a is 5. Well, now let's look at this. A was e to the x, so it must be then that e to the x is minus 8, or e to the x equals 5. Well, that's not possible. Remember, an exponential is always greater than 0. So here now to solve this, we take the natural log of each side and get x is equal to the natural log of 5. Now that's one way to do that. Here's another way. The other way is just look at this and factor it from the start. And when I say from the start, write this as e to the 2x plus 3e to the x minus 40 is 0. And then this just factors as factors as e to the x times e to the x, and then plus 8, and then minus 5. So you can just factor it directly, and that is equal to 0. So this gives you e to the x equals minus 8, the same thing we got above, which isn't possible, or e to the x equals 5, which leads to this. So either way, if you want to try this substitution, if that makes sense to you, you generally let u equal the term in the middle, or you can just factor this directly. You can factor it as it's written. Problem 5 now, solve for x. We're trying to find x. So look, I've got a log equation. At some point, I'm going to have to rewrite things as an exponential. So first thing I'm going to do is subtract 3. That gives me 4 log of x minus 2. And if I subtract 3, I get 44. Now divide by 4. Natural log of x minus 2 is equal to 11. So now I'm going to write this in the equivalent exponential form. This is ln. That means the base is e. The exponent is 11. And that equals x minus 2. So x is equal to 2 plus e to the 11th. Now solve for x. I have the difference of two logs, so this is going to be log base 5. X plus 3, x minus 4 equals 2. Now there's nothing else to do, so I'm going to write the equivalent exponential. The base is 5. This over here alone by itself is the exponent, and that's got to equal x plus 3 over x minus 4. Now 5 squared is 25, so I'm going to write that as 25 over 1. I'm going to write that as 25 over 1, and now cross multiply. That gives me x plus 3 is equal to 25 times x minus 4. X plus 3 is equal to 25x minus 100. So that's 24x is equal to 103. So x is equal to 103 over 24. So there's, excuse me, there's the first page of this little set of problems I discovered. And that took me about 5 minutes. You're using just a handful of properties, and I think those are pretty straightforward. I wouldn't be surprised if something exactly like that or something very, very similar appeared on the exam. Okay. Well, we have another page. We have another page here. So I'll give you a second to get a good look at that. You might want to do a screen capture or something, print that off maybe, perhaps. So I'll give you time to look at it. So now we have some trig problems. And again, very, very straightforward problems. We've done quite a few of these. Let's begin with number 8. The cosine of 0 is 1. Just think of a unit circle. Just think of a unit circle. 1, 0. So when the angle is 0, cosines are x's, so the x is 1. Sine of 0 is 0. Now, cosine of 4 pi over 3, negative. The reference angle is going to be the cosine of pi over 3, plus or minus. So that's going to be plus or minus 1/2. Which is it going to be? Well, I don't know. Where is negative 4 pi over 3? Here's negative pi. That's negative 3 pi over 3, so it's in that quadrant. And the cosines are positive. So therefore, this is equal to positive 1/2. We can pick the plus because it's in... Oh, that's wrong, isn't it? Cosines are negative. Oh, man, I messed up. Cosines are negative in this quadrant, so this is going to be a minus 1/2. Oh, geez. My goodness. Sine of 3 pi over 4. Well, the reference angle is the sine of pi over 4, except plus or minus. Now, where is 3 pi over 4? Well, here's pi, and pi is, of course, 4 pi over 4, so it's here. Now, let's see if I can get this one right. What are the y values in quadrant 2? Well, they're positive. So this is going to be a positive square root of 2 over 2. Cosecant of 7 pi over 6. That's going to be the cosecant of pi over 6 plus or minus. So where is 7 pi over 6? Well, here's pi. Pi is 6 pi over 6. So 7 pi over 6 is in quadrant 3. Remember now, this is going to be 1 over the sine of pi over 6. And down here, the signs are negative because sines are just y values. So this is negative 1 over 1/2. So this is minus 2. Tangent of 5 pi over 3 is going to be the tangent of pi over 3. So where is 5 pi over 3? Well, here's pi, which is 3 pi over 3. Here's 2 pi, which is 6 pi over 3. So that's right there. Now the signs down here are plus and minus. So the signs are different, which means this is going to be minus the tangent of pi over 3. When the signs are different, the tangent's negative. So that's going to be minus. Now, what is it going to be? It's going to be the sine of pi over 3, square root of 3 over 2, divided by the cosine of pi over 3, which is 1/2. So this gives me a minus square root of 3. That should be money in the bank. You should be able to do that as good as anybody. You should be able to do that as good as anybody. Okay? Now let's go up to problem 7. I'm kind of skipping around. You're given that this is the coordinate for a terminal point for an angle on a unit circle. That is so important here. Find each of the following. If it's a unit circle, the y value is sine. On a unit circle, the x value is the cosine. That's like stealing money. What's the tangent? The tangent's going to be this divided by this. So it's going to be minus square root of 21 over 5 divided by 2 over 5. So it's going to be a minus square root of 21 over 2. The 5's cancel out. Cosecant is 1 over sine, so this is minus 5 over square root of 21. Now, nowhere in the directions does it say to rationalize, but I'm going to. So that's a negative 5 square root of 21 over 21. Secant's going to be 1 over the cosine, so that's 5 over 2. Tangent's going to be the reciprocal, cotangent will be the reciprocal of tangent. So minus 2 square root of 21, or a minus 2 square root of 21 over 21. My goodness, folks, that's the easiest thing we've done all semester. This was a unit circle. On a unit circle, the sines are just the y values and the cosines are just the x values. That is stealing points. Okay. Now, let's look at number 9. We want the inverse cosine of a half. Inverse trig functions are angles. So you're being asked the question, what angle has a cosine of a half? And you got to remember the domain of the inverse cosine is the top half of the circle. So what angle has a cosine of a half? Well, that's pi thirds. Okay, cosine of pi over 3 is 1/2. What angle, this is an angle, what angle has a sine of square root of 3 over 2 and it's negative? Well, now remember, for the inverse sine function, the domain are those values. Okay, if that was a positive square root of 3 over 2, we know the answer would be pi over 3. It would be here because the sine of pi over 3 is square root of 3 over 2, but the negative means it's got to be down here. So this is going to be minus pi over 3. Inverse tangent. Inverse tangent only makes sense here. Now this is 1, so you're being asked the question, what angle has a tangent of 1? Well, what angle has a tangent of 1? Plus 1. So it has to be in a quadrant where both x and y are positive. So that's going to be pi over 4. The reason it's pi over 4 is because the sine of pi over 4 is the same thing as the cosine of pi over 4, and when you look at the tangent of that, you get 1. Now look at D. D is a little bit different than these others. So here's what I'm going to do. I'm going to let this junk here be A. So this problem becomes the cosecant of A. Boy, I wish I had a little more room. So I'm setting A equal to the inverse sine square root of 3 over 2. So that means that the sine of A is the square root of 3 over 2. Now draw a triangle. Here's A. The sine is the square root of 3 over 2. So this has to be a 1, doesn't it? 2 squared is 4. 1 squared is 1. The square root of 3 squared is 3. So 3 plus 1 is 4. So now look at what I'm being asked to find. I'm being asked to find the cosecant of this angle. Well, the cosecant's 1 over sine. The sine is square root of 3 over 2. So this is 2 over the square root of 3. Okay? And of course, if you want to rationalize that, it's 2 square root of 3 over 3. Doesn't matter to me. Express cosine in terms of sine if you are in quadrant 3. So let's write that out. If I'm in quadrant 3, x and y are negative, which means cosine is negative and sine is negative. So I want to write cosine in terms of sine. Well, I'm going to use the identity cosine squared t plus sine squared t is 1. So I want to end up with cosine equals. So I have cosine squared t is 1 minus sine squared t. So cosine of t would be plus or minus 1 minus sine squared, taking the square root. So which is it, plus or minus? Well, we're in quadrant 3, and the cosines are negative. So that means my answer is cosine of t is minus the square root of 1 minus sine squared. So what gave me that minus was where I am. I'm in quadrant 3. Okay, and again, just remember, inverse trig functions are angles. All right. Let's see what's next. Okay, we're going to do some graphing of trig functions, it looks like. So I'll give you a chance to take a screenshot of that, or just follow along with me, however you want to do this. Okay, now it says you're given this, and we want to call off the information. What's the amplitude? Well, the amplitude would be the absolute value of minus 6. So the amplitude is 6. The amplitude is always the absolute value of whatever number that is. The period, well, the reference curve is y equals sine x, and it has period 2 pi. So the period is going to be 2 pi over 5. Okay? So whatever that number is, put it in the bottom. So the period is 2 pi over 5. That means over any interval that's 2 pi divided by 5 units long, you get one complete sine curve. Now the phase shift, well, remember the general form is A sine of k x minus b. That's the generic form. In this problem, k is 5, so it's 2 pi over k. And the phase angle is b when it's written as a minus. So this is x minus a minus pi over 8. So the phase shift is minus pi over 8. Or you would shift the curve pi over 8 units to the left. Okay? Now it looks like in number 12 we're back in exponentials, and it looks like we want to draw all this stuff. So what I'm going to do right down here, I'm going to draw the reference. Now the reference curve is 2 to the x. The reference curve has that shape. Okay? So in our discussion, I'm going to keep track of what that point does. So what does it do? Well, look, if the reference curve is 2 to the x, we've replaced x with x minus 3, that means we shift the curve 3 units, 1, 2, 3, 3 units to the right. So this point here gets shifted to the right 3 units. Okay? So everyone see that? The reference curve is 2 to the power x. This is 2 to the power of x minus 3. So I've replaced x with x minus 3, which means the whole curve gets shifted 3 units to the left. And then finally, the minus 4 means that the curve is shifted. Now this would be 3, 1. The curve is shifted 4 units down, so it's going to be shifted down to 3 and minus 3. So the domain, well, it would be all reals. The range. Okay, now let's talk about this. We've got to be careful here. So this point is going to be shifted 3 units to the right. So it's going to go from here to right there. And then it's going to be shifted 1, 2, 3, 4 units down. Okay? So that's going to be 3 and minus 3, right? Well, see, the exponential function is asymptotic to the x-axis. The x-axis is y equals 0. It's going to be shifted 4 units down. So it's going to be shifted, the boundary line, the asymptote, the horizontal asymptote, is going to be shifted 1, 2, 3, 4 down. So this thing is going to look like this. That's the shape it's going to have. So the range, now this is y equals minus 4. So the range is going to be minus 4 to infinity. I'm going to get all the y values bigger than minus 4. X-intercept. Now remember, intercepts are coordinates. Intercepts are coordinates. Let's go ahead and do this since we got this. A horizontal asymptote is going to be minus 4. Y equals minus 4. These are coordinates. So the x-intercept, I don't know what it is, but I know the y value is 0. So I'm looking for this number right here. And that tells me that y has to be 0, doesn't it? Let's see if I can squeeze this in. If I have 0 is equal to 2x to the power of x minus 3 minus 4. So I get 2 to the x minus 3 is equal to plus 4. Now I could solve this with logarithms, but notice here that 4 is 2 squared. So I've got 2 to the second is equal to 2 to the x minus 3. Since the exponential function is 1 to 1, I have 2 is equal to x minus 3. So x is 5. So the x-intercept is going to be 5 and 0. Isn't that cool? Now the y-intercept. What happens where we cross the y-axis? Wherever we cross the y-axis, that means x is 0. So if I have f of x and let x equal 0, that becomes f of 0. That's this point. F of 0, if I plug 0 in for x, I get 2 to the minus 3 minus 4. Well, 2 to the minus 3 is 1/8 minus 4. Well, now how do we do this? It's not hard. That's 1/8, and 4 is 32 over 8. So this is a negative 31 over 8. So the y-intercept is going to be 0 and a negative 31 over 8. Isn't that cool? Pretty neat. Pretty neat. Okay, lucky 13. Let's look at problem lucky 13. Let's do the domain. Well, see, the log function doesn't make sense. If we graph a generic log function, it looks like that. So you can only take the log of something positive. So the domain we must have x plus 3 positive. So that means x is greater than minus 3. So this would be minus 3 to infinity. Now the range, well, see, we're just going to get this curve, but we'll come back to it. Let's talk about what happens here now. The reference curve, this is my reference curve, and that is y equals log base 3 of x. That's my reference curve. It looks like this. And this is the coordinate 1, 0. So I'm going to keep track of that coordinate. Well, look what happens. X gets replaced with x plus 3. That means this point is shifted 3 units to the left. So it was here. So there's 1, 2, 3. So this point on the reference curve gets shifted to right here. Now on the reference curve, the vertical asymptote is the y-axis. Well, it gets shifted 3 units also. So 1, 2, 3. See that? So if we shift this 3 units to the left, 1, 2, 3, this is x equals minus 3. So the vertical asymptote is x equals minus 3. Got that? Now finally, the minus 2 does what? Well, we take this point and we move it what? 1, 2 units down. So it's now right here. So what's the curve going to look like? Well, it's going to look like this curve right here, but shifted 3 to the left and 2 down. So it's going to have, now I don't know exactly what it's going to do, but the shape is going to be like this. And I'm going to wait a minute. The shape is going to be like I'm drawing there, because I've got to answer a couple of questions. Well, first of all, you can see the range is going to be from minus infinity to infinity. I get all y values. But now the interesting questions are, what are the x-intercepts and the y-intercepts? Well, let's do it one at a time. At the x-intercept, y is 0. So for an x-intercept, that implies y equals 0. And y is just f of x. So I'm going to set 0 equal to the log base 3 x plus 3 minus 2. That gives me 2 is equal to log base 3 of x plus 3. Wow. Well, now, what do? Okay, think about it. I've used all the stuff I know what to do. The only thing remaining is to write the equivalent exponential. The base is 3. The exponent is 2. So it looks like x is going to be 6. 3 squared is 9. We subtract 3 from each side. So that tells me this thing is going to turn and cross out here at 6. Now of course, that coordinate is 6 and 0. So the x-intercept is at 6 and 0. Okay? Now, finally, what's the y-intercept? Well, to find the y-intercept, you let x equal 0. So we want f of 0. That's going to be the log base 3. Now, if x is 0, look what happens. That's 0 plus 3, which is 3, minus 2. Well, what is log base 3 of 3? Well, that's just 1. So the y-intercept is going to be at 0 and minus 1. Look at that. I got pretty close to it with just a rough hand sketch. Oh, that's fun. That's cool. Okay, now, is there anything else? One more page. Okay, we're going to get to shake and bake. Now, I had a little bleed through, so I'm going to try to fix this a little bit. Okay. All right, which of these do we want to tackle first? Well, I'm going to tackle 16. Okay, I'm going to tackle 16. I want to graph the inverse tangent function. Well, my reference curve is the tangent curve. I'm going to draw the principal branch of the tangent curve. And remember, the tangent looks like this, doesn't it? So essentially what I want to do is turn the page sideways. See, I've got vertical asymptotes at x equals minus pi over 2 and x equals pi. So when we talk about the inverse of a function, we swap x and y. So this one has vertical asymptotes. So the inverse tangent is going to have horizontal. So instead of it being x equals pi over 2, it's going to be y equals pi over 2. And it's going to be y equals minus pi over 2. All right, now let's discuss this. As we get close to pi over 2, the y values go to infinity. Okay, so let's write that down. As x goes to pi over 2, y goes to infinity. Well, on the graph of the inverse, we swap x and y. Now, look, there's the point 0, 0, and if we swap the coordinates, it doesn't change. So look, on the reference curve, the tangent curve, as x goes to pi over 2, y goes to infinity. That means as y approaches pi over 2, x goes to infinity. So it's going to do this kind of deal here. And similarly, as x goes to minus pi over 2, y goes to minus infinity. So swap x and y. So there's your curve of the inverse tangent. One of my favorite curves, and this function and this curve appears an awful lot in calculus, more than it should. More than it should. So, remember this graph. You'll need it in calculus. So, okay, we've got a couple of problems left, and let's see, which one do we want to do? Let's do the top one. Let's do this problem here. So, I'm given this cosine curve, and I want to analyze it. Well, I know that the reference curve, I always draw my reference curve. The reference curve looks like this, doesn't it? Over 2 pi units. So the period is going to be 2 pi divided by k. K is 1/2. So the period is 4 pi. Okay, the phase shift. And remember, what we want to do, we always want to make sure this is factored out. We want that x to have a coefficient of 1. When that x has a coefficient of 1, this is your phase angle. So your phase angle is what? Pi. So it's going to be shifted pi units to the right. Well, what are the maximum points? Well, that's going to be the amplitude. The amplitude is going to be the absolute value of 3, which is 3. So the maximum points. Now it says points. It says points, doesn't it? And minimum points. Well, the biggest value of the function is going to be 3. And the smallest value of the function is going to be minus 3, isn't it? But see, the way that's worded, I'm not sure what they mean. We may have to come back to this. Now, x-intercepts as points. Okay. Now, one way to do this is to reason the following. For x-intercepts, we know that y is 0. So if I put a 0 right there, I get 0 is equal to 3 cosine of 1/2 times x minus pi. Cool? Now divide by 3, so we get 0 is equal to the cosine of 1/2 x minus pi. But now what do you do? Now what do you do? Well, I want to show you an alternate. Now I say it's alternate. It looks different, but it's the same thing as this discussion. And look, what I want to keep in mind is the reference curve, and the reference curve is the cosine curve, which looks like this. So that's 2 pi. Now what's this? Where is the cosine 0? Well, it's 0 at pi over 2. Where is it 0 again? Well, it's 0 again at 3 pi over 2. And the minimum point occurs at pi. This is minus 1. This is plus 1. So I'm going to do just this. I'm going to take this and set equal to each one of these and get all the information. So where does the curve in the problem start? Well, this tells me it's been shifted pi units to the right. So instead of starting at 0, it's going to start at pi. But look, I'm going to confirm this. So the start, I'm going to take 1/2 x minus pi and set it equal to 0. This is what happens on the reference curve. The reference curve begins at 0. Multiply each side by 2 gives you x minus pi is equal to 0. So see, I get the same information. This curve starts at pi, right? Now, this is the first time the reference curve is 0. So the first x-intercept, I'm going to take the argument 1/2 times x minus pi and set equal to the first time it's 0 in the reference curve, pi over 2. Multiply by 2, you get x minus pi equals pi. So x is 2 pi. So the first time this curve intersects the x-axis will be at 2 pi. It begins at pi, and the first intercept is at 2 pi. Well, what's the second intercept? I'm going to take 1/2 times x minus pi and set equal to 3 pi over 2. That gives me x minus pi is equal to 3 pi. X is equal to 4 pi. So the second time it cuts the x-axis is going to be at 4 pi. And finally, where does it end? Well, you can guess what I'm going to do. I'm going to take x 1/2 times x minus pi and set equal to 2 pi. Now multiply each side by 2. X minus pi is equal to 4 pi. X is equal to 5 pi. Now I'm just going to use that information to sketch the curve. It's going to begin, I'm going to call that pi. It's going to begin right there. And I need to go up, this is 1, 2, 3. I'm going to go up to right there. So it's going to begin at plus 3. So when is the first time the curve's going to cross the x-axis? Well, it's going to cross the x-axis the first time at 2 pi. So I'm going to go pi. and then that's going to be 2 pi. And let's just go ahead and mark this off. 3 pi, 4 pi, 5 pi. So it starts at pi, and the first time it crosses is going to be here. The second time it crosses is going to be here. And then at 5 pi, it's back up here at 3. Well, what happens between 2 pi and 4 pi? Well, it's going to be down here at minus 3. So it's going to go like this. Okay? Now, what are the maximum points? Well, the maximum points are going to be pi and 3 and 5 pi and 3. The minimum points are going to be at 3 pi and minus 3. Now you say, wait a minute, how do you know that occurs at 3 pi? Well, look, on the reference curve, the minimum occurs at pi. So I'm going to take 1/2 x minus pi and set equal to pi. That's x minus pi is equal to 2 pi when I multiply by 2, and then x is equal to 3 pi. So at 3 pi, I'm going to have a minimum. Now, what's going to be the x-intercepts as coordinates, as points? The x-intercepts are going to be 2 pi and 0 and 4 pi and 0. Now notice that the curve starts at pi, the curve ends at 5 pi. Well, 5 pi minus pi is 4 pi, which matches this. See? Where it ends minus where it begins is the period. Okay? Notice I get the phase shift. The reference curve begins at 0. So I set this argument equal to 0, and this tells me where the curve starts. So this reference curve, it begins at 0. My new curve begins at pi, so the phase shift is pi units to the right. Cool, I think we got one more problem. We want to graph f of x equals 3 cosecant. Well, okay. To graph the cosecant function, I have to graph the sine curve. The sine curve begins like this. Okay? That's my sine curve. Now, this is at 2 pi, this is at pi, and this is at 0. And the reference curve is the sine, and it goes from 1 to minus 1. But look, I've got a 3 right there. So all I'm going to do is label that 3 and minus 3. So here's what I'm going to do. I'm going to go 1, 2, 3. 1, 2, 3. And then very lightly, I'm going to draw in my sine curve. So here's pi. Here's 2 pi. Now this is pi over 2, it's up here. 3 pi over 2, it's down here. So I'm going to sketch in very lightly a sine curve. Now, the cosecant is going to be 1 over sine. That's the definition. So here's my sine curve with amplitude 3. So what I'm going to do is put in the boundaries. So everyone see what I'm doing. At pi and 2 pi, the sine is 0, so it's undefined. So these are vertical asymptotes. So the graph of cosecant, 3 cosecant is going to be like this. Okay, and this is 3 minus 3 and then plus 3. And it says label the asymptotes. Okay, so this is x equals 0, x equals pi, x equals 2 pi. And there's the graph of one complete cycle of 3 cosecant x. Okay, I hope this helps a little.